Hello everyone, welcome to this course, Organic Spectroscopic Analysis. In this lecture, we will continue the previous class to learn UV visible spectroscopy. In last class, we have talked about the UV spectra of aromatic compounds. Then let's look at the dye-substituted and multiple group effects of aromatic compounds. With dye-substituted aromatics, it's necessary to consider both groups. If both groups are electron donating or withdrawing, the effect is similar to the effect of the stronger of the pool groups as if the molar substituted ring. If one group is electron withdrawing and one group electron donating, and they are parallel to one another, the magnitude of the shift is greater than the sum of both of the group effects. For the case of substituted benzoyl derivations, the empirical correlation of structure with observed lambda maximum has been developed. This is slightly less accurate than the Woodward-Fisher rules, but can usually predict with an error of 5 nanometers. Additionally, solvent must preserve in the fine structure while it's actually observed in UV where possible. Hydrogen bonding further complicates the effect of vibrational and rotational energy levels on electronic transitions, dipole-dipole interacts, etc. The more nonpolar the solvent, the better. This is not always possible. As for polynuclear aromatics, when the number of fused aromatic rings increases, the intensity for the primary and secondary bands also increase. For heteroaromatic systems, spectra can complex with the addition of the N to pi star transition and the ring size effects and are unique to each case. The portion of the electromagnetic spectrum from 400 to 800 nanometers is observable to humans. We and other mammals have the adaptation of seeing color at the expense of great detail. When white light passes through or is reflected by the surface, those that are observed are removed from the transmitted or reflected light respectively. What is seen is complementary color. Those are not observed. This is the origin of the color wheel, as shown in this picture. Organic compounds that are colored are typically those with extensively conjugated system, typically more than 5. For the example of beta-carotene, lambda maximum is at 455 in the far blue region of the spectrum. That is observed. The remaining light has the complementary color of orange. One of the most common class of colored organic molecules are the azo dye. From our discussion of dye-substituted aromatic chromophones, the effect of opposite groups is greater than the sum of the individual effect, more so on this heavily conjugated system. Coincidentally, it's necessary for these to be opposite for the original synthetic preparation. These materials are some of the more familiar colors of our environment, such as pale red, fast brown, and sunset yellow, bright blue, royal blue, orange red, lemon yellow, and so on and on. In the biological sciences, these compounds are used as dyes to selectively stain different tissues or cell structures, for the example of blue-rich gallets. In the chemical sciences, these are acid-base indicators used for various pH range. Remember the effects of pH on aromatic substituents. We can also calculate UV absorption showing atoms, those molecular orbitals contribute most to the bands by theoretical calculations. Now you may ask why we should learn this stuff. After all, nobody solves structures with UV anymore. One thing is clear. UV can be very non-specific. It's hard to interpret exact at a cursory level and to say that spectrum is consistent with this structure. Each band can be a superposition of many transitions. Generally, we don't assign the particular transitions. Quantitative analysis of UV follows the Beer's law. Relationship between percent transmittance and absorption is the following. A equal to the log reciprocal of T. Light must be monochromatic. Path length must be constant. Sample should not be fluorescence or phosphorescence, scatter light and change its chemical composition. Experimental details include make solution of concentration low enough that A is smaller or equal to 1. Even though a dual beam goes through a solvent blank, choose solvents that are UV transparent. Can extract the epsilon value if concentration of a molecule and B are known. UV bands are broad because vibration levels are superimposed on UV. Modes of spectrometer operation are as follows. Firstly, scan. Acquire a spectrum characteristic of new materials. Secondly, time drive. Acquire A at 1 lambda as a function of time for quantitating kinetics and chromatography. Wavelength program. Acquire A at selected wave number values, quantitation of mixtures, characterization of mixtures. How to perform quantitation using a linear calibration curve. Prepare a series of solutions containing the analyte in the concentration range expected. Record the absorbances for each solution. Plot the area versus absorbance. Measure absorbance of unknown. It's based on the assumption, no sample matrix or chemical species and concentrations. Analytical figures of merit include accuracy, precision, detection limit, sensitivity, dynamic range, practical, time, cost, sample preparation required. The purpose of the method of standard addition is to make standard using complex matrix of sample of unknown composition. Make 2 measurements. Spike sample with concentrated analyte standards. Spike equal to add sample amount of concentrated solution. Principle of additivity is that absorbance of a mixture at lambda 1 should be the sum of the absorbance of the components of lambda 1. Problem solving here. Analysis of mixture containing 2 components. A 1 millimolar solution of a dye A shows an absorbance of 0.2 at 450 nanometers and absorbance of 0.05 at 620 nanometers. And 0.1 millimolar solution of a dye B shows 0 absorbance at 450 nanometers and absorbance of 0.42 at 620 nanometers. All measurements were made in a 2 mm path length cuvette. Please calculate the concentration of each dye present in a solution that exhibits an absorbance of 0.38 and 0.71 at 450 nanometers and at 620 nanometers respectively. A 1 cm path length cuvette is used for both measurements. So for the answer of this question is as follows. That's for today's class. We have finished the chapter of UV and visible spectroscopy. Thank you for watching.